So welcome everyone to another OCP tap call. This is call number 104. We have Madura today here giving us a presentation. So starting with introducing Madura. Madura has held her position across engineering and product marketing in semiconductor industry. Focus at Epson is on optical networking and data center segment. She holds a MS degree in electrical engineering and a bachelor engineering in telecommunication. So today's talk is about the latest trends in crystals and oscillators. So with no further ado, Madura, the floor is yours.
Thanks, Ahmad. Hi, everyone, and thank you to the OCP Tap community and to Ahmad for inviting me to be your speaker today. Really excited to be a part of your group. If you guys don't mind, I'm going to stop the video. I'm having some network issues on my end. Yeah. Right. So we've all worked with or been involved with timing devices in one form or another, either as timing device manufacturers or board designers and embedded engineers utilizing them in their design, and even as consumers. So today, I want to give an overview of what crystals and oscillators are and what are the trends that are driving them for future generations. So let's start off with an introduction to crystals. So crystals are a building block for most timing devices. So oscillators increasing in complexity from simple packaged to all the way up to oven-controlled. So they're used as a basis for all of it. So what is the technology behind it? It's this thing called piezoelectricity. So in the late 1800s, they discovered that quartz generates an electric charge when it is subject to mechanical stress. They also found that this effect was reversible, meaning that it can alter its shape slightly when you apply an electric field to it. But it wasn't until mid-1920s when it was actually used for timekeeping purposes. So initially it was used for radio transmitters and for timekeeping because these were more reliable than the mechanical clocks that were being used at the time. Then World War II happened, and they saw a need for more precise frequency control in communications and radar systems. So quartz crystals and oscillators found widespread use in these applications. Then later on in the 60s, when the advent of ICs happened, we saw miniaturization of these oscillators and crystals, and with surface mount technology, it propelled them to a wide variety of applications as well. Now, coming to present-day devices, these are ubiquitous, and they're found in a variety of devices from IoT and wearables. We're seeing a lot of improvements in stability, and they're also being integrated with ICs and into a lot of advanced electronic devices as well. The image here is to show natural quartz versus synthetic quartz. So reason we use synthetic quartz, better control, better natural quartz is a natural resource, so it's not abundant in nature. So creating synthetic quartz will also give you control over, manufacturability as well, and you get to control the purity of the crystals. And this one here shows the different cuts of the crystal. So we'll talk a little bit more about this as we talk about crystals. So starting at the very basic crystal. So you can divide them into two camps, your kilohertz crystals and your megahertz crystals. So kilohertz crystals, also called tuning fork crystals. You can see over here, it looks like a tuning fork that musicians would use to tune their instruments. So this is the cut of the crystal, and the vibration mode is left-right. And megahertz crystals are typically AT cut crystals. And this is a thickness shear AT cut. So if you want to imagine the vibration mode of these AT cut crystals, imagine you have jelly between your hands and you're rubbing your hands in opposite directions. So that's the vibration mode there. So as a designer, if you're considering a crystal, some of the specifications you would probably put more emphasis on would be size and ESR, which is the equivalent series resistance. We'll talk a little bit more about this in the upcoming slides. load capacitance, drive level, frequency tolerance. So these are some of the specifications that would be more, that you'd put more of an emphasis on if you're looking at what crystal to design in for your system. Coming to ESR. So ESR is an electrical representation of the crystal's mechanical losses. ESR, for the most part, is determined by the size and the frequency of the crystal. So since it's largely dependent on frequency and size, smaller sizes tend to have higher ESRs. But too high an ESR value, and it could cause slow startup and unstable oscillation. So you need to fulfill the right ESR value to achieve stable oscillation in crystals. This here is kind of showing, depending on the size of the crystal. So this orange one over here is a 1210 size, which is the smallest available here. And you can see the ESR is really high for the same frequencies compared to the other sizes there. So why do we care about having a lower ESR? Right? So I talked about how ESR is needed to maintain a stable oscillation, but it also helps in reducing the power consumption, because lower the ESR, the lower your losses, and that enables a longer battery life. And if you're looking at applications such as battery-driven wearables or IoT devices or medical devices, saving on power consumption plays a big role in choosing the right components. And besides power consumption, it also helps with, a shorter startup time. So when you're working with microcontrollers, microprocessors, having a lower ESR also reduces your startup time as well as giving you a lower voltage drive. So now we move on to crystal oscillators. So with crystals, they're basically passive devices, but they require an external oscillation circuit in order to make that work with the rest of your circuit. Crystal oscillators take the engineering out of trying to figure out how do you find the right load capacitance, is the ESR value correct for your design, and they integrate it with an IC and make it more plug and play. And oscillators are also, they vary in complexity. So you can have a simple packaged oscillator, or you can have a temperature controlled, an oven controlled, a voltage controlled. So depending on your application, that complexity increases as well. So now we'll talk about low noise oscillators. So it's hard to mention low noise oscillators without talking about jitter, because that's such an important metric when you're mentioning low noise oscillators, right? And I'm sure most of this group is aware of what a jitter is, probably much more than I am. But as a very basic term, I think jitter is the variation of a signal's timing from its ideal value. And they're typically caused by noise or other disturbances in the system. Some contributing factors may be thermal noise, power supply variations, device noise, or interference from nearby circuits. There's also a few different ways or a few different kinds of jitter, and you can see that in the table over here, from random, deterministic jitter, or phase jitter, which would be a common metric if you're dealing with networking or working on oscillators where noise is an issue, and total jitter. So some of these might be very familiar to you. Oh, sorry. So random jitter is an intrinsic noise. So it's always present, and you can refer to it as like a background or a terminal noise. And this is definitely a significant contributor to overall jitter. Deterministic jitter is more specific. So it has a cause. It could be caused by crosstalk with interfering signals, or switching power supplies, or simultaneous switching of high-speed outputs. Phase jitter, which is what you would often find on a datasheet for an oscillator, is the integration of phase noise over a certain range of frequencies. So these are typically expressed as femtoseconds or picoseconds. So that's the unit of measurement there. So where phase jitter or jitter is a time domain term, phase noise is its frequency domain counterpart. So these are inherently related. And the goal for any designer is to keep these two to a minimum. And you can see on the bottom image over here, it's showing a typical frequency spectrum of an oscillator's output signal, where FC is the carrier frequency. For phase noise plots, we typically show one sideband of the signal from F0, and the noise is plotted logarithmically. The phase jitter would be the area under the curve calculated across a specified bandwidth. So a popular integration bandwidth would be 12 kilohertz to 20 megahertz. It's used quite frequently in networking, but that depends on the application. It's not a hard and fast rule. So here's an example of how phase noise and jitter could be represented on a data sheet. You have your jitter values here. You might show either a typical value or a max value in picoseconds or femtoseconds, depending on the oscillator, and phase noise at the different offsets. So usually random jitter and deterministic jitter are represented in some way, even if they're not outright specified under the phase jitter term. And these are always calculated in a lab with clean power supplies. Why I mentioned that, I'll come to it in a few slides. So it's not possible to talk about jitter for low noise oscillators without talking about applications like networking or optical devices. And here it shows how jitter has evolved from a few years ago with 10 gig, 50 gig, and then the speeds kept increasing with 100 gig, and then your PCIe applications, all the way to 1.6T now. So you'll see how the jitter requirement has kind of become a fraction of what it used to be, like a few years back, from 500 femtoseconds for a 50 gig optical device to 25 femtoseconds to 20 femtoseconds is what we're seeing for 1.6T. And a large part of this for 400 gig and 1.6T to 1.6T is the AI demand that's driving the demand for high-speed optics in data centers. So we're seeing that increase in port speeds go from 400 to 800 to 1.6T. And we're seeing that ripple effect in some of the other networking devices as well. So if you're looking at co-packaged optics, like density, the amount of density that a device can handle, there's a lot of importance being placed upon that. So here we're seeing how timing changes with the clock. So lower jitter, but another factor that's also being influenced is the higher frequency, and we'll come to that too. Now, jitter is not the only attribute being impacted with each new generation of networking device. We're also seeing miniaturization. So smaller and smaller form factors are being required with each new generation. And a large part of that is because we're using the same, for example, QSFP-DD or OSFP modules, but the density is increasing. So when your board density is increasing, your board space is constrained, which makes you're cramming a lot more components into the same space. So when this happens, your components are also getting hotter. So one, you're reducing the form factor of your devices, and also your operating temperature range for these timing devices are also increasing. A few years ago, we were at minus 20 to 70 C, and then it went to minus 40 to 85 C. But now it's minus 40 to 105 C on the higher end. And I think in the near future, it will probably go up to 125 to match what we're seeing in the automotive industry now. So in addition to seeing these changes in form factor or the jitter requirements or operating temperature, we're also seeing a requirement for higher frequency as well. So if you're using a fundamental oscillator that are out in the marketplace today, 156.25 megahertz was a pretty common, Ethernet or networking frequency. And with all the changes that are happening with port speeds, we're seeing that increase to 312.5 megahertz or 625 megahertz. And a lot of times it's easier to go with like a higher fundamental frequency because you do get a 20 log n reduction in jitter when you're reducing that multiplication factor. So that's another trend that we're seeing. So I mentioned that we're using clean lab or clean power supply in our lab to measure jitter. And this is why a lot of times we don't take into account how your oscillators might work in the real world condition. So as it wasn't an issue, a few years ago when your jitter budget was not as tight as it is now. But I think moving forward for all these 1.6T or 3.2T or co-packaged optics, your PSNR plays a big role as well because you want to see how it behaves when it's introduced to noise. So one way to measure that is have a baseline, take 3 devices here, and you're looking at, with no supply noise injection, what would that phase noise curve look like? And then we're introducing a 20 millivolt sine sweep, and we're injecting that noise from 400 kilohertz all the way up to 1.4 megahertz, and noticing how they behave under these different noise injection frequencies. So for example, here, device B is more sensitive to the lower frequency of 400 kilohertz, but device A and device C don't show that much of an impact until you get to some of the higher order magnitude frequencies. So PSNR, one way to kind of improve numbers would be integrating LDOs with your oscillator to provide for a clean and stable output.
I
So a
am
lot of
hearing, I am
networking.
hearing lots of, I am hearing lots of in the background noise. So somebody really is causing this noise. Can you mute yourself?
Thank you for that. Yeah, I think it's a lot quieter now. Yeah, thank you. So on the networking side, a lot of them typically end up going with a differential output option for their oscillator. And one reason is, of course, the jitter performance. So if you're looking for the best jitter performance that you can get out of an oscillator, one is definitely going for a differential output, and two, choosing the right kind of differential output. So your LV-PECL has a really wide swing, so you would get the lowest jitter out of that output. But if power consumption is something that you're worried about, then I think LVDS would be the way to go. HCSL is a very common differential output option that's used by Intel and by PCIe SIG. I think it's because of its compatibility with CMOS. So these are the 3 output options that are out there for low noise oscillators. So jitter is just one aspect of going for a more complex oscillator. So if you're going for one step up from a crystal to a oscillator, jitter is one of the metrics that you would look at. The others would be frequency deviation. So frequency deviation is, in an ideal world, your crystal or your oscillator wouldn't deviate with temperature fluctuation. However, crystals are sensitive to temperature changes, and these temperature fluctuations would lead to frequency deviation. Too much of a frequency deviation, and it would raise concerns about safety and reliability, and would lead to incorrect timing or measurement errors or just inaccurate data. And it's typically defined within a maximum temperature range. So on the low end, it would be your minus 40 C to a high end of, depending on your application or the segment that you're working with, 125 to about 85. This graph here shows the behavior of the crystal, and it's also dependent on the cut angle of the crystal itself. So you can see this one over here is closer to about 5 ppm or 10 ppm, and this one over here is 50 ppm. So it deviates depending on what is the temperature that you're working with, and also the cut angle itself. Now, frequency stability is another metric that you'd probably be familiar with if you work with some of the higher stability oscillators. It's defined as the maximum allowable deviation over temperature and listed as ppm, parts per million, or ppb, parts per billion. So the frequency of this crystal could change either due to the operating temperature range, it could change due to humidity or aging. And typically, if you're looking at a data sheet, a lot of manufacturers would list this separately as well, like whether a 1-year aging or a 10-year aging. And some of the other specifications you might see might be frequency tolerance. So frequency tolerance is that maximum allowable deviation from that nominal frequency, but this is measured at room temperature at 25 C. And there's also frequency over temperature characteristics or frequency stability, which is the allowable deviation from a nominal frequency, but this is within the operating temperature range. So not just at 25 C, but within a given, say, minus 40 to 85 C. So that's how much would it deviate? So that's what it would measure. So when you need a device with really high stability and your standard oscillator falls short of that desired level of stability, you would go with something called a TCXO, or a temperature compensated crystal oscillator. So how does this TCXO work? They typically have a compensation network with a built-in temperature sensor, which detects temperature changes. And once it detects that temperature change, there's a pulling network which will translate that change into a controlling voltage. And this will translate that temperature change into controlling voltage, and the voltage compensates for the frequency deviation that happened because of the temperature change. This graph over here represents that really well. So this blue line here is your frequency deviation because of temperature changes, and this red one here is your compensation circuit providing the controlling voltage, and the yellow is your compensated deviation. So this is what you receive as your output. So for TCXOs, I think we're all aware of its applications in 3GPP and GNSS modules, but they're also used in a wide variety of other segments. So they're used in IoT gateways, smart meters, or in consumer devices with smartwatches and wearables. They also find a lot of uses in networking as well with NIC cards, switches, servers, and routers. So taking a step back from talking about oscillators and going back to talking about the cut angle of a crystal. So we talked about AT cut and tuning for crystals earlier. AT cut is what's called a temperature compensated cut. SC cut is a stress and temperature compensated cut. So AT cut is what we've looked at so far in all the other oscillators. And SC cut we're bringing up because we're going to go into a more complex kind of oscillator called an oven-controlled oscillator. So I wanted to give you guys a look at what an SC cut is. So some of the key distinguishing factors between these two is the frequency versus temperature, where you would see a minimal change in frequency over a wider temperature range for the SC cut. They're also known for their excellent temperature stability. And yeah, as I mentioned, they exhibit minimal frequency change. So this makes them really ideal for high precision applications. So I'm talking about PPB and up. They also have generally favorable aging characteristics, which means their frequency stability remains high over longer periods of time. And they also display a higher tolerance to external stresses. And this makes them really reliable and stable in varying environmental conditions. So while TCXOs and OCXOs both provide exceptional stability, the main difference is also in the complexity of the components that are used in the circuit, as well as an extended stability or the effects of aging. So where TCXOs find use in applications like smartphones, GPS devices, base station applications, OCXOs are better for communication or network applications that need a higher precision and also a better long-term stability. So there's two kinds of OCXOs. One would be it's called a discrete OCXO, and the other one's an integrated. Discrete OCXOs are standalone components that would need an external circuitry to be integrated into a system. These are useful in high precision applications where utmost accuracy is essential. Integrated OCXOs, on the other hand, are designed to be a part of a larger integrated circuit or a module, and their compact size makes it really easy to integrate into more space-constrained electronics while also providing a high level of performance. So how do these OCXOs work? So you take a quartz crystal and you heat it to a specific high temperature inside a thermal enclosure throughout the duration of its use. And this is done to reduce the frequency variations It also has a temperature compensation circuit to detect changes in temperature, and this will provide feedback to a control circuitry. The control circuitry then works to maintain that temperature with a high level of accuracy. So what would be some of the trends we're seeing in OCXOs? How are they changing with each new generation? Just like the other timing devices like crystals or simple oscillators, these are also following the same miniature organization trend. Miniaturization trend. So they're trying to make them into smaller packages that are closer to that of TCXOs. If you can imagine, OCXOs, I think even now there might be a few that's in use, but they're a 25 by 22 millimeter. So bringing that closer to a TCXO to a 7 by 5 millimeter, you can imagine, how much engineering work is going to go into changing that packet size. Another thing they're doing is also utilizing machine learning to achieve close to 24-hour holdover with 1.5 microsecond drift. The other trend we're seeing is also a versatility aspect. So previously, OCXOs were where the crystals were cut to a specific frequencies and they were programmed to that. So 10 megahertz, that frequency is cut to 10 megahertz, and that's what would be used. But now they're combining them with PLLs to increase the number of available frequencies, and it also makes it easier to ship faster as well. Yeah. Now we'll move from some of the higher stability oscillators and take a look at what's called real-time clocks or RTCs. So while crystals and RTCs perform the same basic function of timekeeping in electronic systems, they serve different purposes and they also have very different characteristics. So where crystals are used to just keep time and provide a clock signal for other components, RTCs maintain accurate time and date information over longer periods and sometimes even without main power supply. They also come with some additional components and features, and that makes it suitable for a lot of applications that need persistent and accurate timekeeping. So some applications are used in our computers and embedded systems to maintain accurate time and date, but they're also used in systems which require persistent timekeeping, like data loggers and network devices, or devices that may need a timestamp, or they may need an alarm function or a wake-up timer, where you can generate an interrupt event set at some cycle. So they come with a lot of these added functionality. So if you're designing an embedded system that needs timekeeping, you have the option of using a MCU with an embedded RTC, or you could use a separate RTC module. So if you're going with an MCU with an embedded RTC, there is an advantage of space savings. So you're combining the processing capabilities of an MCU with the timekeeping functions in one single chip or one single package. But this does come with a limited flexibility. So in the event that your MCU's embedded RTC doesn't meet a specific accuracy requirement or feature requirement, then you may have to look for another external solution. In addition, if the MCU fails, both the processing and timekeeping functions are lost. So having a separate RTC module in this case, or in terms of like critical applications, might actually prove useful. A dedicated RTC module will also provide a higher accuracy and stability. And a lot of times they come with features like temperature compensation and lower drift over time. And that makes them suitable for applications where precise timekeeping is critical. In addition, a lot of them are also equipped with battery backup capabilities. So to make sure that the timekeeping is continuous, even when the power supply is off. So here you can see how long your backup supply would last on an MCU versus, say, a dedicated RTC module. So lots of IoT applications, I think, would find this very useful, having a battery backup, as well as automotive applications as well. Just to kind of add on to the previous slide where you have a power switch with a backup supply. In case your main power supply fails, the RTC would switch to its backup battery automatically instead of your timekeeping being interrupted. So improved time stability is another advantage of using a dedicated RTC module. So they typically come with a much higher time accuracy compared to an MCU with an embedded RTC. So what are some of the applications these would be used in? Consumer industrial, they find a lot of widespread use. They're used for their backup power supply, their timekeeping, they're also low power consumption. And for a lot of the IoT modules that are out there or surveillance and smart meters, board space is limited. So this compact design also supports that limited board space applications. Automotive is another segment where RTCs find a lot of use cases, especially the low power consumption and how it maintains the clock accuracy over the higher temperature. So we talked about temperature ranges in networking and for TCXOs and OCXOs. Automotives generally run a lot hotter, so their operating temperature range is minus 40 to 125 C on the higher end. So it helps having something that would maintain that accuracy even at the higher temperature ranges too. So, I think that's all I had for you all today. I hope you got an overview of what crystals are and how they translate to working with oscillators and the increasing complexity of the different oscillators that are out there, and some of the trends that we see out in the marketplace today. Thank you.
Thank you. All right, so let's open the floor for questions.
So, Ahmed, I have some questions.
Go ahead, Hisham. Go ahead.
So, thanks a lot, Madura, for the presentation. But I am just thinking about outstanding problems that you think still need to be addressed related to using crystals for time synchronization. Like, for example, sometimes I think dynamic non-linearity and the behavior of the oscillator may cause some problems. There might be problems related to scalability, jitter, frequency, phase offset, noise, interference, and so which one of those you think is still outstanding and require further research to be resolved?
Are you asking about those in relation with
yes,
a specific application?
No, in general.
Yeah.
Not a specific application. What
Right.
Crystals are used for timing applications and time synchronization, but there are issues that
Maybe we can rephrase it so that what are the existing challenges
exactly
that
yes
yet you still think majority think like the community should look into?
exactly. Thank you, Ahmed.
You're welcome.
Yeah. Thanks, Hashim and Ahmad. Yeah, so there are certainly a few challenges, and I think the industry, whether all of us, I think, are working towards. One is definitely improving on the accuracy of the systems, your stability, for one thing. Jitter is always a constant struggle, I think. I mean, in an ideal world, customers would love zero jitter, but that's not possible. So I think bringing it as low as possible. Miniaturization, I think, in some applications is definitely a concern because there's definitely a physical limit when you're working with crystals or any other device. How small can you go without impacting performance? So that's another area that I think we're working on improving.
Mm-hmm. So miniaturization is not your friend, basically.
It is, but I think it depends on the application because not every application needs it to be smaller than it is now. So, for example, the use cases of IoT would vary greatly from the use cases of, base station timing requirements. So I think it's also very segment related.
I have a question. This is Ramki for Madura. Long term, how do you see the crystal oscillator coexisting with MEMS technology? right? Because there's a lot of buzz around silicon oscillators and how rugged they are, small. Of course, power consumption is all a wash. I think very similar. I mean, crystal might be even better, but I think I'm hearing a lot of noise about MEMS-based silicon oscillators. How do you think these two technology can coexist, and will one or supersede the other, or they have their own places in the market?
Yeah, that's a good question. And I get asked that a lot, working for a quartz supplier, right? I think they've been around for so long. I mean, quartz has been around for decades now, and they both have their strengths. So MEMS, I think, does better on, say, vibration, for example, and that might be useful in applications like weapons, or where you need accuracy of less than like 1 ppb. So, but it would be overkill if you're looking at, say, clocks or IoT modules or, gateways and routers. So they both have their applications where I think they have a strong foothold, and I think that'll continue to be so for upcoming future. Although I feel like in the future, I'm sure more developments are going to happen, whether on the IC side or whether on the quartz side. So it'll be interesting to see how they improve, but I definitely see them coexisting.
Thank you.
Ishan, go ahead.
Thank you, Madura. That was a wonderful presentation. Enjoyed it thoroughly. I have a question regarding when you talk about temperature, there's a notion of a static temperature and the temperature changing. Can you give some insight as to how these devices behave with a temperature slope, shall we say, changing temperature?
Yeah, certainly. So I think when people measure the frequency over temperature characteristics, I believe that's what you were referring to. It's a static temperature change, or it's like a slow temperature change, right? So it's in a controlled environment and you're really testing, say, 1 degree C, 2 degree C up over a certain controlled period of time, but that's not a real world condition. Some oscillators behave better than most. I think TCXOs put a lot more emphasis on the frequency or temperature slope for sure. So with how to withstand sudden changes in temperature as opposed to, say, just a crystal or a simple oscillator. So certainly dependent on the kind of timing device that's used.
If I can follow up with another one is, can you make some comments regarding any of the random noise? I mean, you have the deterministic, which would be aging and temperature, but just random noise, what kind of noises can we expect from TCXOs versus OCXOs? In terms of, for example, TVAR or TDEV.
Yeah. I think with TCXOs and OCXOs, it's also dependent largely on the manufacturer too. I mean, some of it is your resonator dependent, some of it could be your PLL dependent. So that really depends on how it's being designed.
Thank you.
Right, we told.
Thanks, Kishan.
Thank you very much for your presentation. I have one question that is of serious interest to me. It is, would you be able to share any data on your best clocks and their behavior in space, specifically low Earth orbit, not geosatellites, but LEO satellites?
Yeah, we would be able to, but I think that might have to be offline to share about a specific product, figure out what the application is and what your requirements would be.
Thank
But
you.
yeah, as a general, I think the TCXOs and OCXOs are probably what would play into that field, just because of the accuracy requirements.
And totally different environment than you will face on the planet, on terrestrial
Certainly.
networks.
Yeah.
So I have a question, Madura, in the interest of like trending, basically in the interest of what mainly the topic of the presentation is. So is there any like let's say new efforts for different substrates, like let's say moving from like silicon to let's say like uh, other substrates like gallium arsenide, I don't know, or other things like is there anything done in that field or not? Or like GaN even, gallium nitride.
Yeah. I think that might be a question that maybe my MEMS counterparts could maybe answer, because we deal mainly with the quartz resonator for sure. But I'm sure everyone's looking into it to see if there's alternate materials that could provide improved performance.
So the second part again, going toward like the trending, uh, how is it? How are the things like, again, the trending in terms of oscillators for this for built-in synchronization and like in general? Like I see that, for example, with bigger modules, that they receive, let's say, PPS input and they figure something out and so on. But like, do you have an insight on like how things are trending on that field?
Yeah, I think as a very basic understanding of that would be one is certainly improving the performance, and I think Kishan talked about like the frequency slope. I think that would be one area of improvement for this. The other one would be, you know, your accuracy itself. I think these two will probably be areas where you would need improvement if you're looking at synchronization.
And probably the last one from my side is, let's say you've been in this field for years and like working in like, you know, directly with like what as let's say a vendor and working with customers. Let's say fast forward in 20 years. Again, you're not responsible. It's just like what do you imagine? Like what do you think like things will change? What are you going to still like, you know, like provide as a vendor? What do you think?
Yeah, so one area, I guess, like my prediction would be either TCXOs being as stable as an OCXO, or OCXO kind of like that line between the two merging further. You see the OCXOs becoming smaller and competing with TCXO. So maybe there's like a area of opportunity there where you can get that current consumption under control, and provide that higher accuracy so that it could be used in some of the more currently TCXO dominated applications. But I mean, I could be wildly wrong, so don't quote me on that.
Yeah, that's fine. Of
But
course.
yeah, I think that's one area where I see the lines kind of blurring a little. And I know someone else asked about, you know, like where MEMS and quartz kind of coexisting, and I think that'll continue to happen. I don't think either of them are going away anytime soon. I think they'll just find their niches moving forward, or I think improvements in IC and driver capabilities will bring about a massive change in performance for both quartz and MEMS, I'm sure.
I wish I had someone from TI. I don't think anyone is here from TI. Is there anyone from TI? I wanted to also see like what do you think like about, let's say, technology like BAW, like this microwave based technologies, like how is that coming together? It would be great if someone else also can add to it. Kishan, your hand's still up. Do you have something to add?
For me,
Kishan.
Sorry.
uh,
Yeah.
Oh, okay.
yeah, but Ahmed, I had a comment to what
Yes, please go ahead.
we told made a good question about satellite using crystals for satellite, and on Monday meeting in the other work stream, the TSIAW work stream, David was talking about using quantum transfer for time synchronization between satellites, and we didn't talk much about oscillators, or the characteristics of the oscillators that can be used in quantum time transfer between satellites. So if we told have some insights on this, please let us know.
And Madura, like Kishan is asking if you can put your contact here so people can get
Yes,
you.
we will discuss it later. There's lots of interest, lots of developments, not necessarily what we heard today, but alternatives and some new developments that are happening in fractional type of ideas and fractional quantum that is maybe very useful. Thank you.
So maybe you can present this in a future meeting.
Perhaps, yes.
Thank you.
Thanks, Kishan. I've shared my email address in the chat, so please feel free to ask me any questions, or if you have any questions on the presentation or would like to know more, I'm available.
Maybe you can put the slide that has the thing, because I don't think the chat will go on the recording. So
Here. I think I didn't include that slide. I'm just going to move the chat to the screen that's recording.
So another question, I don't know if you have the answer for it, is how do you see with like like oscillators, let's say, with technologies, let's say like trending technologies, let's say quantum entanglement or things like that. Like, do you see like the oscillator directly, like let's say playing a key role with, like we have like oscillators that are entangled, let's say. I don't know if you have the answer for that or someone else can add to that.
I have to admit, I'm not very knowledgeable about that, but I think in the networking, we are seeing a lot of more optical switching coming into play. And a large part of why they don't want to include too many timing devices is because the clock data recovery is, when it feeds into the DSP is definitely a power-hungry little monster in the optical modules. So it'll be interesting to see how oscillators evolve in that space, as well as like the quantum entanglements as well. I think there's definitely a shift coming there, but I'm not sure which way it would go yet.
Is anyone else like want to add a comment on that?
Yeah, just a comment. I like this idea of looking at physics packages, quantum entanglement, atomic clocks. You have all of them are not natural oscillators. So you always will need some kind of an oscillating mechanism which is somehow locked to that physics package. And that's where some of these TCXOs, OCXOs will come in handy, because they are natural oscillating mechanisms. It's just that they don't have the true accuracy or stability of that physics package. So they can, that's how they get their performance.
There is one important thing also that, since you brought it up, is it is important to always consider short-term stability versus long-term stability, in terms of, if you want to have long-term stability, you cannot have, like, let's say when this always comes up, like let's say customers want to aim for, let's say, to be more precise, aim for like zero jitter. If you have zero jitter, you're not going to have good stability, because that means you're not deviating, from what you're doing. Again, like this is from a Fourier transform. So is that into place into consideration or not, like in general?
If I may answer that, the way I look at it is that the oscillator is what gives you the short-term stability, either the cycle to cycle or over a really short term. Whereas the physics package or any other reference is going to give you the longer term stability.
So that is perhaps like that the trending part is not on the oscillator from what you're saying. It's
The
more
oscillator
about
has
the
to be good
module
enough
that,
to support it.
yeah.
Okay.
And Kishan, since you're here, like again, is there something you can add to like what Madura presented in terms of, let's say, other material being explored these days, like let's say GaN or gallium arsenide or any other things, like I don't know, like
No,
there's a lot of
that's not my
limitations.
area of expertise, Ahmed. But
Mhm.
I would like to hear more about it because I'm sure there are other people like from Renaissance. I know that Greg Armstrong is there, so they've had some experience with it.
Mhm.
So,
Yeah, if Greg wants to add something.
Yeah, I don't have anything to add really at hand. I think, yeah, as I said, it's probably better as a presentation. It could be a good topic, but other Galvian that has other things you have to look at compared to silicon, and some of it is around thermals.
Mhm.
Silicon definitely is much better at thermal dissipation than GaN and the GaN. So that's one comment. But there's always transitions. You mentioned BAW. There's many vendors are looking at BAW technology as well, but it has its pros and cons. So I think as Madura highlighted, I think in the end, you're not going to see any one of them necessarily go away. It's going to be probably more focused at the application level of what are the needs, right? Is it
More options.
integration and smaller? Is it stability and deterministic over different conditions and things like that? Each of them have their pros and cons. So I think they're going to find their niche in those type of markets. It's like you said, you're not going to just all of a sudden magically see MEMS out in space and without a reason why, because what's out there already works and is known how it works, and it's known how it reacts to the environment. It's a lot of investment for the MEMS manufacturers to go off and look into that. And vice versa, same with integration, right? There's many manufacturers, even in the crystals, looking at taking concepts of MEMS, more about being silicon based, and they're actually creating new technologies based off actually creating quartz almost like silicon, so that you actually are it's almost becoming much like MEMS, right? Raycon is doing technology like this and others. So I think there's lots of advancements happening, and every market and application is driving different needs of why. And I think you're seeing that even in the data centers, right? Data centers traditionally we're quite happy with crystals and oscillators, but as applications and needs of synchronization and that come, they have to relook at what's available, which they get the advantage of. They could enter some of those new technologies and take advantage of some of those things today, and stuff like that. So. Yeah, I think that's all I'll add, because it's hard to jump in. I don't want this to, I'm not going to jump in as a BAW expert or as a MEMS expert. So I think that would be a good reach out for a topic to see if one of those guys want to come in and present that topic and talk about it. I agree.
Sure, yeah. Like if there is more specifics, please feel free, share it with Hisham or Dan, and they can go like find, like, let's say, or if you have someone directly, you can feel free to just invite them to this.
Yeah, Ahmed, I have a quick question
Yes, go ahead.
for Neil, because he knows ORAN. Do you think, Neil, there is a special need or special requirement for crystal oscillators to satisfy the needs of ORAN time synchronization? Maybe Neil is gone.
Hisham, you wanted Greg to answer it or Madura?
Madura or Neil or yeah, Madura, sure. Neil is not here. Madura, sure.
Sure. Yeah, I think for ORAN, you're seeing a lot of advancements happening even now. I mean, ITSF had a lot of papers based on OCXOs and TCXOs for that application. So I think vendors are definitely taking note of what we need to do more in that category. And you're seeing those advancements happen now.
Oh, you are taking care of it. That's good.
All right.
I guess I could just add to that.
Good,
So,
good.
yeah, so again, ORAN itself is not new, right? It's just bringing the radio access network into an open architecture. So the usage of temperature-based oscillators, OCXOs, and VCXOs, voltage controlled. All these capabilities have always been there and have been integrated into systems for a very long time at the radio or within the base station or as part of the transport. What I think you're seeing is much what we're highlighting is you're seeing the integration, right? Instead of having discrete circuits to get both, ultra low phase noise along with synchronization, along with short-term stability, along with long-term stability. They're trying to find ways to get that stuff integrated either into silicon, into crystal oscillator circuits in their technologies or MEMS or whatever, right? So I think that's what you're seeing and so that's why you're seeing all these kind of mishmash of technologies coming in because people are trying to find ways to combine the technologies, right? So, BA has, had an application that it was used for, but they're realizing maybe there's applications for it in wireless, right? TCXOs traditionally were used kind of as intermediate nodes, just offering maybe short-term stability, not necessarily long-term. But because of OCXOs, as Madura highlighted, being smaller, people are saying, well, why can't I have longer stability at the radio? Why can't I have integrated circuits there that are giving me durations of hours of some sort of stability as opposed to minutes and stuff like that? So I think what you're seeing is what ORAN is introducing is because they're trying to open up the architecture of the radio access network, people are looking at with the segregation of some of that equipment, the needs of certain requirements are moving. They're shifting. They're not all focused right at the BU or sorry, the baseband unit, like the source of the clock and all that. The source is now being distributed. So it's opening up different type of requirements. So I think that's why you're seeing all these little trends happening. It's not because it's new. Like I said, TCXOs have been around for many years, right? They're used back in PDH days of network and digital, right? So back in the 80s and 90s, right? So they're not new, but what you're seeing is just they're evolving to maybe more into different markets that maybe they weren't necessarily popular for because they didn't quite meet the needs. But phase noise is becoming very important, especially in wireless, right? And you get into MIMO and all these different technologies of that into microwave and talked about space, right? So these are all driving all this, right? So I don't think it's ORAN is driving these requirements. I think all you're seeing is there's more discussion saying, hey, why can't we do things more smartly as opposed to all these discrete vendors coming out saying, well, I have a solution for the radio, here it is. And no one really even knew what was inside it, right? Now people are trying to say, well, what is inside there? And could we do something better as opposed to reuse existing technology? So I think that's where what you're seeing ORAN is driving is the open discussion of, is there better ways to do certain things?
All right. We're on top of the hour. If there is no further question, we'll adjourn and we'll see you in 2 weeks. Oh, Bijan, you want to add something?
Oh, no. All I was going to say is we have an Evenstar project here at OCP. And you guys were talking about Open RAN. We're building an open radio platform, much in the form of, SAI, what SAI did for networking. They're doing it for open radio. And yes, synchronization is really focus area because ultra reliable, low latency communications is not possible unless you have ultra synchronization. So that's all I had to say.
Wonderful. All right. See you in 2 weeks. Bye, everyone.
Thank you.
Bye.
Thank you all.
Thank you
Bye.
very much. Bye-bye.